Hello Internet, my name is Quinn and this is Blondihacks. Working on my A3 locomotive this week, we're going to make the steam manifold, the main steam manifold for the cylinders. This is quite a complex structure, there's a lot of plumbing and some other really cool features in this thing that I think you'll like. So let's go. This area between the cylinders is where the main steam manifold goes. It's a T-shaped piece. The steam is injected down into it from the boiler and it comes out here through these holes in the frame and goes into the cylinders. Then the exhaust goes back out the other way. The manifold bolts directly to the cylinders through these holes in the frame, so everything is sealed and connected without the frame interfering with anything plumbing-wise. You might be thinking this would simply be a series of plumbing pipes. Maybe we're going to start with copper tubing. No, in fact, we're going to start with a big old hunk of brass. This manifold is a giant T-shaped piece of solid brass. And the reason is that it isn't just conducting steam in and out of the cylinders, it's also conducting heat into the cylinders. One of the main jobs of the steam manifold is to help keep the cylinders hot. This is of course important for a steam engine because if the cylinders are too cold, then the steam will turn into water vapor or even worse, liquid water when it hits those chilled cylinders. So the big beefy manifold is physically touching the boiler at the top, as you'll see, which allows it to conduct heat down into the cylinders and help keep them hot. As you can see, I started with a big chunk of brass square bar milled to slightly rectangular dimension, and now I'm milling out a channel for a smaller piece that will be silver soldered into place. This would be much too big a structure to mill out of a solid piece of brass, so we're doing a silver soldered assembly here. Then I'm also milling out some pockets on either side of that. These are just clearances for accessing the bolts. As you'll see how this all goes together, the bolts would be nearly impossible to install. They're already very difficult to install, even with these clearances, but they would be impossible without. Once that's done, I flip that over and do the same clearances on the back as well, because there's mounting bolts top and bottom to clamp this structure to the insides of the cylinders. That's all looking pretty snazzy. We should be ready now to assemble this into a T-shaped structure. That other little piece that I machined to size to fit in here is going to get silver soldered in there. And it's a fairly loose fit by design because we want clearance for silver solder to go all the way down around that joint. We need to fill that whole area so this becomes a solid T-shaped structure. To help with that, here's a trick I learned from Kozo. Put a series of center punches around the piece, and that will effectively suspend it in space, leaving just enough of a gap all the way around for silver solder to flow down into all of those areas. It's a bit of a tight fit now, so I'll tap that into place right before soldering, but this is a really good technique to ensure that you get a good quality joint on all the mating surfaces. Into the pickle bath then with those chunks, and we'll get those cleaned up, ready for soldering. This is a hefty assembly with a lot of mass, so I've got the big torch set up. We're going to need lots and lots of heat for this. People often watch me silver solder assemblies like this and assume I'm using too big a torch, but that is incorrect. The size of your torch is dictated by the mass of the pieces that you are soldering together, not the size of the joint. A small torch, a precision flame, which people assume would be easier, it does not get the assembly hot enough. You'll never get that solder to flow correctly, and you'll never get it to make a good joint all the way down through all of the mating surfaces. Just like electrical and plumbing soldering, the secret to silver soldering is the mass of the pieces must melt the solder, not the torch flame. So here I'm heating the joint almost entirely from below, so that as the brass itself heats up to the melting point of silver solder, then that solder starts to flow. And the heat of the two pieces of brass draws that solder down into the joint all the way down through that entire U shape into all of those areas. A little help from the patented Kozo scratch rod is also a good idea to make sure that the solder flows nicely. That looks like that went really well. I did have a little bit of an issue. I didn't get quite enough heat on the back, so I do have what could be a gap there. Just to be sure, I did another soldering operation on this side. I didn't point the torch around the back very much, so that didn't get quite as hot because I couldn't do that without endangering the camera. You see the things that I do for you people? Well, that's not going to win any beauty contests for soldering, but it did clean up just fine, so I think we're ready to move on. Next up, the steam intake pipe gets machined directly into the top of the T as a fitting. So I'm going to mark the location for that on the surface plate. center punch that, and then I'll get that center punch mark centered up on the lathe. In addition to centering that mark, another really important set of alignments here is that the T-shaped piece has to be aligned longitudinally. It might be a little crooked because, well, A, it's a silver soldered assembly, so it's probably not going to be perfectly square, and B, this 4-jaw chuck is frankly not awesome at holding things square. The chuck jaws on this thing they're very playful, which is to say, I mean, there's a lot of play in them. So after dialing it in concentrically on that punch mark, I'm then going to check the alignment of it longitudinally on a couple of surfaces, and you can see that it's, sitting pretty crooked in those jaws. That is de rigueur for this inexpensive chuck. So I'll do a little bit of tapping in to get it straight. And in this case, this near side to me needs to come out of the jaws a little bit to get that straight. So this is a technique that works well for that on small chucks where you can't get a hammer in behind the part. A little bit of lever action with a punch. You can tap one side of the part outwards like that. And I did that until I had the piece running straight, or, at least within 1,000th or so of straight. That'll be sufficient. And then, of course, that straightening action messes up the concentricity of our punch mark, so I go back and dial that in again, and you might have to go back and forth a couple of times on a part like this. We're going to be drilling a hole all the way through this part. It's a very, very long, deep hole. And so the piece has to be sitting very straight, or else that hole is going to come out crooked on the other side. Now I can turn that plumbing fitting that I was talking about. A person could, in principle, make this plumbing fitting as a separate piece and then solder it into the top of the T, but I think Kozo does this as all one piece because that way there's only one joint in the entire assembly. I think it would be fairly difficult to solder a plumbing fitting into the top of this without damaging the T-joint at the bottom. So doing it with just one joint and then machining all the other features into the assembly I think makes a lot of sense. So after turning that down, I'll now cut some threads on the outside that will be where the main steam pipe coming from the boiler attaches to the top of the T. This is where the steam is going to be going down into the manifold to be sent over to the cylinders. To that end, then, of course, we'll need a hole all the way down the center of this thing. That's what will make this into an actual plumbing fitting and not just an elaborate chunk of brass that we've machined because we apparently don't have anything else to do with our day. Now, this is a very, very deep hole. It's what we call a high aspect ratio hole, which is to say it's much, much deeper than the diameter of the drill. The aspect ratio of this hole is something like 50:1. So when drilling a really deep hole, the tendency is for the drill flutes to pack up with chips. Drill flutes have an efficiency on them that is limited by the diameter of the drill. So the smaller the drill, the quicker the flutes pack up. So when you're drilling a small diameter hole really deep like this, you need to pull the drill clear very, very frequently to clear chips. If you don't, what'll happen is the chips pack up on the end and they start pushing the drill sideways and your hole will come out crooked. A really fast way to clear chips is to just periodically release your tailstock, pull it clear, push it back in, and resume cranking. After doing that, I've got an indicator set up on the tailstock quill so I can drill a very accurately depthed counter bore. This is for the plumbing fitting that will ultimately be attached here. And that is it for the lathe work on this piece. We can take it down. Got a bunch more holes to drill, but that was the one that we really needed to do on the lathe because of that turning that needed to precede it. You can see that hole came out in just the right place, so that went well. Next to that is the exhaust port, and this I decided to do on the mill because we don't need to do it on the lathe. There's no turning involved before making this feature, and this is going to be easier for me to do on the mill rather than having to set that piece up centered on a new punch mark on the lathe. The drawings actually suggest doing all of these holes that we're doing on the lathe. I think if you don't have much of a milling machine, or if you don't have a milling machine at all, that makes perfect sense to do this on the lathe, but for me it was easier to do it on the mill because of the size of the machine that I have and the capabilities that it has. There's never one best set of operations or order of operations for making a part. It's always dependent on what your machinery is capable of, what tooling you have, and so on. With both those holes drilled, now I can do some inspection. I want to make sure that there isn't a gap where the two pieces of the T meet. If that solder hadn't flowed all the way down under there, I could have a cross leak between the passages or a leak to the outside from one of the passages. But it all looks good in there, so now we can go on to the side passages which connect and make this into an actual manifold. These just get drilled straight in from the ends. You'll notice in all of these passages that the intake passage is small and the exhaust passage is large. That's because, of course, the intake steam is at high pressure, and the exhaust is at a lower pressure, lower temperature, so it needs more room to get the same number of moles of gas out of the cylinders. You always want to match the intake and exhaust, of course, just like on an internal combustion engine. We also have some clearance holes on the ends, and these are how the manifold gets bolted to the insides of the cylinders through that house-shaped opening in the frame. Moving on to the underside now, we need to enlarge those intake and exhaust passages to receive a couple of really interesting mechanical components. This isn't just a steam manifold, it's doing a couple of other jobs as well. So we have some fittings that need to go in the bottom for those jobs. So for that, we're going to get clearance from the tower for this setup, and then put some counterbores on the underside to receive those fittings. You'll see what those fittings look like in a second. I think they're really, really cool. Probably the coolest part of this whole assembly. Those fittings are bolted in place, so we drill and tap some holes on either side to affix those. The next job is to shape the ends so that they fit through that house-shaped opening in the frame that we saw at the top of the show. I'm going to lay this out on the surface plate as kind of a sanity check. I've actually done the trigonometry to figure out how much I need to remove from each corner, but it's nice to have a layout line to kind of sanity check what you're doing as well. Conveniently, these are all 45-degree angles, so the setup is pretty easy as angle cutting goes. I can use a simple little 45-degree square, set that up like so, and mill straight down the amount that the trigonometry told me I need to mill down. Conveniently, I can do the same corner on both ends in each one of these setups. So we have 8 of these corners to do, but only 4 setups are required. Also convenient, once the first side is done, then we have a parallel reference on the bottom of the part, so I don't need the square anymore. I can just land it on those angles that we've already cut, and cut the other sides parallel to those. Here is the funky little shape that we've created, and this is essentially a clearance shape to fit through those house-shaped openings in the frame. I was really, really hoping that I would have some way of wiggling this into the frame without needing to dismantle the frame. And sadly, the answer is no. There is no way to get that in there. So I did in fact have to take the entire frame apart, which included removing the wheel sets, dismantling the axle boxes, and a whole lot more work that I didn't bother showing you, just so I can test fit this and see if those angle cuts were all correct. And that fits in there very nicely, as you can see. The opening is house-shaped essentially because it needs to sit as far forward as it can, but we want to leave lots of material around those bolt holes because, of course, all of the horsepower of the boiler is getting transmitted through the material around those bolt holes and into the frame and into the drivers. So we do want as much material there as we can, and the house shape helps ensure that. Over to the lathe now to start on those cool fittings that I talked about that go in those holes in the bottom. There's 2 of them, and they both start the same way by making kind of a T-pin shaped thing on the lathe. And Yahtzee. Centering it up now on the mill with my coaxial indicator, I'm holding it vertically in a collet block. This setup is going to allow me to do pretty much all the rest of the features on these 2 parts, so this worked out really well. Now that I'm all centered up, I can do the bolt pattern that bolts the fixture into the bottom of the T, as you saw earlier, those threaded holes that we made. These get countersunk, so the screws will sit flush. Properly countersunk screws is one of those things that just never gets old. That is just always beautiful. I don't know why, but I love that. Now I can machine the sides of this flat. These pieces have kind of a pill-shaped base, as you can see from the pictures in the corners of the screen. And that will allow the 2 fixtures to sit next to each other and not overhang the sides of the steam manifold. So that's looking pretty good. We got a couple more features to do, but I'm going to pause there and go back to the lathe and make the other one because it needs all the same setups. So I'll Yahtzee that off. You'll notice this one has a thicker base on it because I got to flip it around, do a second operation, and put a threaded plumbing fitting on the back side of this one. I'm intentionally not telling you what these fittings do because it's going to be cool. You'll see. Hang on one second. Next, I've center drilled that, and we need a very, very tiny hole all the way down through the center of this, but I'm not going to drill it because look at the size of the drill that I need to use. Now, my lathe only goes to 800 RPM, and a drill this small needs to run at least 3,000 or 4,000 RPM. 6,000 or 7,000 would be better. My lathe does have a higher belt setting, but that belt is a pain in the butt to move, and even on the higher setting, I only get 1,800 RPM. So I've center drilled that to mark the position of that hole perfectly concentrically, which the lathe is very good at doing, but then I'm going to drill that hole over on the milling machine because my mill can do 4,400 RPM, which is much more in the ballpark of a drill this small. That all seemed to be going well, except, well, let's look at how these pieces go into the manifold itself. The first one that we just made slides in nicely, as you can see. The other one, however, the base of it is actually smaller in diameter, and the bolt holes are supposed to be closer together on the smaller fitting. And, well, I didn't get that right. I misread the drawing and I made the bolt pattern the same on both fittings. So this little disc here is too small. I can't get the clearance holes in the right places. Rather than remake the entire steam manifold to correct that error, I just made this fitting piece again with a larger base on it. So it'll look the same from the base as the other fitting does. It won't be smaller as the drawing has them. With that little error worked around, I brought the base of this one to the same point, and now we're ready to drill that tiny, tiny through hole that I talked about. Got the mill cranked all the way up to 4,400 ripms, and away we go. Now with a drill this small, this is actually a PCB drill to give you a sense of how small this thing is. To get a hole this tiny drilled all the way through a piece this long, again, it's that hole aspect ratio problem, this time to an extreme degree. So I'm doing very tiny cuts and clearing chips extremely frequently. Some people call this peck drilling, and basically doing lots and lots of pecking. The nice thing about a small milling machine like this is you have really good feel on the quill. You can feel when the drill stops cutting, and the moment it stops cutting, you got to pull that clear the chips, and then go back in for a little bit more. And as the hole gets very deep towards the bottom, you might only get 10 or 20 thousandths of additional cut before the flutes pack up and you got to clear again. So you're going to be doing a lot of clearing. Then once again, this gets a counterbore in the top for a plumbing fitting that will be attached to this. Okay, enough with the suspense. This piece with the tiny hole in it is an oil injector. The way that steam engine cylinders are lubricated is by injecting oil into the flow of steam somewhere along the way. Kozo's design does this by creating this injection needle for the oil system. The mechanical lubricator on the locomotive injects oil through this piece with a 90-degree point on it that deflects the steam at the bottom of the manifold to both cylinders on either side, and in that same moment shoots a little bit of steam oil into the flow. It's a really nice little design that does multiple jobs. Over to the other piece now. This one is set up vertically, and I'm cutting a couple of curved features in the end of it with a ball nose end mill, because this is an exhaust deflector. The exhaust coming back in from the sides of the manifold needs to go up the chimney, up the top of the manifold, and without some kind of encouragement, the two exhaust passages on the cylinders are just going to backfeed into each other, and it's going to cause performance issues for the locomotive. To prevent that, Kozo designed this piece, which creates a little curved deflector into both exhaust passages and keeps them from being directly connected while sending the exhaust gases smoothly straight up the center passage from both cylinders. I'll show you in a second a little bit more about how this works. I suppose you could file this as well, but I happen to have a ball nose end mill that was the right size, so that was a nice, easy way to create this elegant little feature. You can see it kind of looks like a screwdriver blade. I'll show you how this works here when I install both of these fixtures into the bottom of the T. First is the oil injector that goes onto the intake side of the steam passages. That little threaded fitting on the bottom, of course, will get connected to the lubrication system later on. And then here's the exhaust deflector that we just finished, and that goes into the exhaust side of the manifold. This is sort of like a three-angle valve job for steam engines, if you like. Hopefully you can see with the light hitting that deflector how it creates a curved profile for the exhaust gases to get redirected up the chimney. And then on the intake side, you can see that sharp contrast between the two sides of the sharp angle where the steam will get sent to the sides and that oil will get injected in the same moment. I'll talk more about how the locomotive's lubrication system works later. We've got lots more to do on that, but for now, I'll just give the passages a quick test to make sure everything is working, and that all looks good. Installing everything is tricky. There are 12 bolts and 4 steam passages that all need to line up perfectly. For me, I only needed to test fit this 1 time. Sorry, my thumb was covering the notes. Oh, 10 times. Yeah, about 10 times of taking this all apart, making some slight filing changes to the manifold and putting it all back together were required to get it all to fit. I was able to modify the house-shaped manifold in situ with a Dremel, so I didn't have to take the whole frame apart every time. But yeah, it was a lot of test fitting to get all of that to fit together. But fit together it did, and now you can see the air coming out of the valve chests, which suggests that all of that plumbing that we've done so far is all working together correctly. It's been a while since we've seen the boiler installed, so let's take a look at that on there. Here you can see where the steam is going to be coming out of the main regulator on the boiler and going down into the manifold to feed the cylinders. The exhaust side of the manifold will later get plumbed into the smoke box and send the exhaust gases up the chimney, which also helps create draft for the fire by drawing gases through the smoke tubes on the boiler. The boiler saddle, which supports the front of the boiler, is what will physically connect it to the manifold, which creates that heat transfer that I talked about to conduct heat from the boiler down into the cylinders to keep them hot. Well, it's really looking like a boat now. We've made good progress, I think. We're really getting into the nitty-gritty of the plumbing and the mechanicals on this beast now, which I'm very excited about. I hope you enjoyed watching me make this manifold, and I hope you enjoyed learning about how much this thing is actually doing as much as I did. Steam locomotives are incredibly cool, incredibly clever, and Kozo's design for the model of this one is equally cool and equally clever. Thank you very much for watching. Thanks especially to my patrons for making this happen every single time, and I will see you next time.